welcome back for the third installment of the AP ECE Chemistry Chapter 13, Acids and Bases. Problem set, let's check out problem number 47. In problem number 47, you're told that you're dealing with a weak acid and you're given 2 grams that are diluted to 100 milliliters of solution. You're told that at that point the pH is 2.54 and you're asked to find out what is the Ka. So as usual, my advice is to write an equation. You start with your undissociated acid and equilibrium arrows, because it's a weak acid, to dissociate to the hydrogen ion and the conjugate base of the acid. Then you set up an ice table. Now there's values populating it here, but these values are only put in after the work that we had from the next steps. In part 3, you convert your original given 2 grams of the weak acid into moles and then molarity, and you find out the original molarity is 0.114 molar of this weak acid. That's what populates this original ice thing under this concentration here. This is ICE, initial change equilibrium, and that's listed in molarity. You make the assumption that you have no molarity of your original hydrogen ion and no molarity of your conjugate base. Then you move on to solve out. You're given the pH. The pH is a way to find out what the hydrogen ion concentration is. So you can do 10 to the negative pH to find that the hydrogen ion concentration is 0.00288 molar. Now, if we make the assumption that there's only of the original undissociated acid to start, and it breaks apart into the acid and the conjugate base, that we should get an addition of some small amount plus x for each of the concentrations of these two products, and we should consequently subtract a small amount from their original concentration. Since we know the pH, we know what the concentration is at equilibrium of H+, and since it's a 1-to-1 ratio, we also know what the concentration of the conjugate base is. So we can actually plug in these values of the conjugate base concentration, the weak acid, the H+ concentration, and the weak acid concentration into our Ka expression, which is derived from our equilibrium equation. Plugging those values in, we get a Ka value of 7.6 times 10 to the negative fifth. Let's check out problem 55. Problem 55 is similar to problem number 47. You're given a weak acid. You're told it has a Ka value. You're told you mix a certain mass of it into a certain solution. You're asked to find the pH and the percent ionization. So rather than finding finding Ka as you were in last one, now that we're finding pH. So flipping it around, but same kind of idea. Start by writing an equation. We can include our Ka here. Just good practice to put your Ka right at the end of your equilibrium equations. Then you set up an ice table. Again, I've started to populate it with values in here, but we have to work towards those values. You take your given mass of the phenol and the volume and convert to find out that you have 1.73 times 10 to the negative 1 molar of the phenol. That goes in as your original thing. You know you have none of the hydrogen ion dissociated, none of the conjugate base dissociated, so you'll get a plus x for the change here. You'll end up with x for both of these things, and then your 1.73 times 10 to the negative first molar minus x for your equilibrium concentration of the phenol. You know the Ka, so you can start plugging in those values, and you have x in the numerator, x in the numerator. That's for your hydrogen ion and for your conjugate base. Then you have the concentration of the undissociated phenol here, and you subtract the x from that, but you don't really need to. You can assume that it's 0. It essentially will be 0, and then you solve out for the x. It makes your math a little easier. It's an assumption, but it tends to be correct. And then you can do the negative log of that x, because that x value is what hydrogen's concentration will be at equilibrium, as we found in our ice table. To solve for percent ionization, put the hydrogen ion concentration over the original concentration of the undissociated acid, and then multiply by 100, and we'll get 0.0025%. It's not a very strongly dissociated substance.